Okay, so last time we finished this part, which is about calculating the E field generated by a charge ring. Of course, this problem is feel like some sort of stupid because you're just integrating a constant around the ring, so over the ring. But it shows the concept here is the point here is that when we have a charge which is with a continuous charge distribution, we cannot regard it as a charge particle. So we need to separate into many small enough charge packet so that we can regard each one is a point charge, and then you can calculate the E field generated by each package. Then the next step is to find some symmetry so that you can cancel some of the component. Like this, you can cancel the horizontal component, and then you only need to calculate the vertical component, and then you can just integrate the rest of the stuff. Then it's done. So we finished the sample problem last time. So next is a quick checkpoint. The figure shows 3 non-conducting rods, one circular and 2 straight. Each has a uniform charge of magnetic field. Along is top half and another along is bottom half. For each rod, what is the direction of the electric field at this point? So this is just to let you practice how to cancel some of the components, how to determine which component can be added together. So for the first one, so what is the direction of the E field generated by these parts? So actually, this is a negative charge. So and actually, this is some sort of symmetric. So the E field should point to this direction. Right? Actually, 45 degrees. Assuming that the charges distribute uniformly, and also this is a semicircle. So for this part, this is positive Q. So the E field should point to the top right direction. So in this case, assuming Q, this is minus Q, this is plus Q. So actually, these two E fields should have the same magnitude, and in this case, the horizontal component should be cancelled. And finally, the overall E field generated by this part should point to the positive y-axis. So plus y-axis. For up. So for the part B, what will it be? Which direction should the E field point to? Yeah, I think it is quite trivial, pointing to the right. And how about the part C? A bit more difficult, but actually not so difficult. Yeah, pointing down. So for the upper part, it should point to this direction. Actually, if you just interpolate this line, so it will intersect with the middle point of this rod. But this is not very important. And actually, you only need to know that the E field generated by the upper part should point to the bottom right direction. And for the lower part, it should point to the bottom left, pointing to this port. Because it is negative charge, this is positive charge. So, and actually these two should have the same magnitude, and the horizontal component cancel each other. So the overall E field should point to negative y-axis. This is plus x plus x axis. Any questions? Okay, so next one we calculate the E field generated by a disk, a solid disk. Just now, actually last time, we calculate the E field generated by a ring, generated by a ring. Now this is a solid disk. This is a solid disk, and so we repeat the same procedure. We want to actually cut it into many small units. Maybe you can cut it like, actually it is a actually it is a circle, a disk. So maybe you can cut it horizontally and vertically, so that it may not be a good choice, because for circle using the Cartesian coordinate will make the calculation a little bit more difficult. Just like you calculate the area of a circle, so that you need to calculate the integration like this. Like this. So you need to use some U substitution, x equals r cosine theta, something like that, to really calculate it. So maybe we can make use of the previous case, because we actually can calculate the E field generated by a ring. So we can have many rings with different radius, and then we put them together, so that with many different rings with different radius, then it will become a solid circle, something like this. So in this case, we consider this strategy. The yellow ring is has some sort of charge, has some of the charge of this disk, and also we assume the charge distribute uniformly on this disk. So actually, the charge on each ring is different. For a larger ring, it will have more charge. For a smaller ring, it will have less charge. So, but actually, we start from this one. From the previous case, we have the equation like this. So here, we consider the dE generated by this ring will be something like this. 1/4 pi epsilon naught is the same. Q becomes dq, because it only consists of a infinite small charge here. And if you add all of the small charge together, it's a total charge on this disk. And also we consider the Z from this disk, and nothing special Yeah. Yeah. The overall, the total radius of the this is capital R, but we consider the ring have a radius small r to be a variable because this r should vary from 0 to capital R. To vary from 0 to capital R, so that you finally return out you integrate dr from 0 to capital R. Okay, so we have the expression like this from this one. Actually, this is this one. Equation 2016, this one, which is the if you generate by ring. So we only make a little bit modification, Q into DQ, capital R into small r, because we need to vary the r. We need to integrate over small r. So in this case, we need to really calculate what is DQ with respect to the in terms of small r, small r. And here we assume the surface charge density to be sigma. Last time we assumed the linear charge density to be lambda. Now we have a surface charge density, which means that if you multiply the surface charge density by the total area, it will be the total charge, because the charge is uniformly distributed. So the surface charge density has a SI unit C over meter squared. So in this case, dA, so we have dQ equals sigma times the dA. dA is the area of this ring. Although this ring is very, very thin, which is dr. Actually, we actually we have a circle, and then this is the center, and this is 0 to capital R, so that, and this is the small r axis. So we actually cut the r axis into many small parts, and of course each one is infinite hexagonally stored, so each one is what we call dr, and the area of this ring should be 2 pi r times dr. Why? Because you can assume you just cut it out, and then you expand it, so it will something like this. Maybe I use another color, you can see it more clearly. You can imagine oops, maybe I just draw the outer boundary to be green, so that you can imagine after you expand it out, it will be something like this. So in this case, the length of this circle should be 2 pi r. Actually, you should learn it in primary school. And the height of this rectangle should be dr. So the area of this ring should be 2 pi r times dr. And what we write here is dA. dA is the very small area, and dA should be 2 pi r times dr. So we substitute this one into here. So we have like this. We have expression like this. Actually, we can just rearrange sigma to the front. Well, pi can be cancelled. Yeah. Pi can be cancelled. Sigma to the front, Z to the front, and keep 2RdR here. 2RdR here. So when you when in the calculus class, you know that dr square is 2RdR. 2RdR. So we can use this substitution to solve this integral. So so actually we want to calculate the overall E field generated by the whole disk. So we need to integrate dE from 0 to capital R with this expression. So we substitute this expression dE equals this one into here, so that we only need to deal with this integration. So this integration, this term to the 2/3 power, 3/2 power at the denominator, which means that it is negative 3/2 power. And just now I just mentioned dr square is 2RdR. And if you just add a constant here, you d a constant is nothing but 0. So this one is actually this one. Okay. So now it will be very easy. You can just regard this one is a whole, and then you can use you can just integrate xn dx, which is nothing but n plus 1 x no integration n plus 1. Of course, if it is an indefinite integral, it should have a plus c, but here we have a definite integral, so that we don't really need to plus c here. We only need to substitute r and 0 into this expression, and then we subtract them. So this is minus 3/2 power. So plus 1 should be minus 1/2 at the denominator. And this power becomes minus 1/2 power. So finally, you substitute r into this expression to replace the small r. So we have z squared plus r squared. Take the square root at the denominator. And then you substitute 0 into this expression. This one becomes 0, and then you only have z squared, take the square root, which will be 1/z, which will be, this one will become 1/z. So finally, z, and then you multiply to the front. No, you distribute the c into here and here, so that z and z will cancel. So we have 1 here, and then we have z over square root of z squared plus capital R squared. The expression will be something like this. So any question? Any questions? Okay. So we derive the E field generated by a charge disk. It looks a bit complicated because the terms here is is a large term, but it will we can derive it with this assumption, which means that when R, capital R, tends to infinity, it will lead to a very beautiful expression. And actually, you will see it again. You'll see it again in the coming chapter. I'm not sure the next chapter or the chapter 25 for the capacitor. For the capacitor, you will see this again. You'll see this again. So actually, the point here is that if R tends to infinity, means that these disks become infinitely large, and then this E will become a constant. It is nothing to do with the Z. Very, very strange. So it only related to how many charge on the disk, or the charge density on the disk. And then epsilon 0 is a constant, 8.85 times 10 to minus 12. So this is a constant. Regarding to the space, to the z-axis. And you say, how about the xy axis? It will be also a constant because this is infinitely large. So then when you move to the different xy direction, then it will be the same. But this is still very, very large. You cannot escape from the disk. So it is a constant in the space, constant E field. So actually, if the charge is positive, the E field will point to the upper direction for the upper part, and pointing to the lower direction for the lower part if Q is positive. If Q is negative, if Q is negative, then the E field will point to this direction. E field. So there are two cases. It's either positive or negative. It's zero. If it's zero, there's no E field. So this is quite an important equation, I think, although it's not very, very simple. So this is an application for the parallel plate. So here, assume that we, if a particle with charge Q is placed in the external E field, and electrostatic force act on the particle, F equals QE, which is the definition at the very beginning of this chapter. So assuming that if the Q is positive, and if the Q is positive, then if this plate is also positive and the upper plate is negative charge, so the E field, well, no, I think it's not, Q is not positive in this case. I think Q should be negative for this case. But if Q is the positive case, it is the other way around, but it already drawn the direction of the E field, so Q should be negative for this case, and the plate here, the lower plate should be negative, the upper plate should be positive, so that the E field point to the lower direction. And in this case, the force, because Q is negative, so the force of the charge should point to the upper direction. So within this area, the force acting on this charge should point to the upper direction. And in this case, at the very beginning, the charge is shoot out horizontally, and then it will bend to the upper direction, and then shoot on the paper, This is the theory of the inkjet printer. So it tried to make the ink with some sort of charge, and then you try to control the amount of charge on the ink, and then you will try to go to the desired places, and then you print out what you want to print. So next one, we have a sample problem. Okay, so the question is a little bit long. Yeah. So the deflecting plate of the inkjet printer with a superimposed coordinate axis. An ink drop with a mass 1.3 times 10 to minus 10 kilogram, and a negative charge of a magnitude Q enters the region between the plate. Initially moving along the x-axis to the actually the right-hand side, the x-axis, with the speed vx. The length of each plate is 1.6 centimeter. The plates are charged and thus produce an E field at all points between them. Assume the field downward directed uniform has a magnitude 1.4 times 10 to 6 Newton per Coulomb. What is the vertical deflection of the drop at the far edge of the plate? The gravitational force can be neglected. Actually, you can calculate if you would like to, but we will assume that force is very, very small compared to the electromagnetic force. So first of all, we would like to calculate watch. So first of all, we'd like to calculate the time of the charge, which will be within this area. Charge time, we call it capital T. T would be nothing but 1.6 centimeter, which is 0.016 meter, and then divide by 18. 18 is the velocity, which means that S equals Vt. So this is Vx. So this is 8.89 times 10 to minus 4 second. Because the force acting on this charge will always point to the upper direction. So there's no force acting on the horizontal direction. So the horizontal velocity will not change. So that we can calculate the time of the charge, which will be within this region. So the next step is to calculate F equals QE. I need to change the picture. So the force acting on it will be F equals QE, which will be nothing but 1.5 times 10 to minus 13 times 1.4 times 10 to 6. So you just need to plug in the number and it will all be done. So it will be 2.1 times 10 to minus 7 Newton. So maybe I just add another page. So finally we have y. We have y equals 1/2 at squared. I suppose you should have learned it in high school. So which will be 1/2 f over m t squared. So t is 8.89 times 10 to minus 4. 8.89 times 10 to minus 4 square 1/2. F is 2.1 times 10 to minus 7. 2.1 times 10 to minus 7. And then m is 1.3 times 10 to minus 10 here. So actually this is nothing but 64 times 6.4 times 10 to minus 4 meter, which is 0.64 millimeter. Or more correctly, you can write it as 640 micrometer. This is something like the scientific prefix. Actually, you can have a quick check for the metric prefix. Yeah, the metric prefix. So then we have quite a lot. So we have tera 10 to 12, giga 10 to 9, mega 10 to 6, kilo 10 to the 3rd. So I suppose all of these used to be very familiar as long as you use the computer. You very familiar with this one. You don't really need to memorize them. So milli, I suppose you also should know about that, millimeter, which is 10 to the minus 3 power. And I suppose you really need to memorize quite a few, up to 10 to minus 15, So 10 to minus 6 is micro. So this is a Greek letter M, of M. So it is mu. So milli to mu, easy to remember. Nano is 10 to minus 9. So when you consider the nanometer process, nanometer CMOS, nami, which is this one, which is 1 billion of 1 meter， 1 million of 1 meter， 就是把1米切成10亿份，那1份就是1个纳米。 And Pico is 10 to minus 12. When you use some, maybe use some capacitor, it would be picofarad, something like this. And femto is 10 to minus 15. 10 to minus 15. When we talk about some time, we may use this femto, but actually not really. But actually, these 4 or 5, 1, 2, 3, 4, 4, I think you should remember them. Okay. So next one, dipole in an electric field. Just now, actually, last time we have I've mentioned what is a electric dipole. Which means that there are two charge with the same magnitude but negative sign. One is plus q, one is negative q with a very small distance, and they are stable to hold together. So it is a electric dipole, and we can define a vector to describe it. The direction is from the negative charge to the positive charge, and the magnitude is nothing but the charge q multiplied by the distance between them, which is qd, and d can be regarded as a vector which has the same direction with the dipole. So now we define another value called the torque. I suppose you should have learned this in the physics 1, the torque, which is 力矩. So it is nothing but the P, which is the electric dipole, cross with the electric field, which means that if you have a dipole in this direction and the electric field is pointing to the right side, then the dipole will rotate. Why we like this? Because for this positive charge on this E field, the E field points to the right, so this one will have a force acting on this. There will be a positive. There will be force acting on this positive charge to the right side. And for this negative charge, as it is negative, the direction of this force will point to the left side, and the two forces will be with the same magnitude but the opposite direction. And also they are acting on two different points. This one at this point, this one at that point. So if you can simply imagine that something stretch this point to the left side and stretch this point to the right side, then it will rotate. So in physics, we will describe this phenomenon using the torque. And actually, torque is a vector. So as long as you know the right-hand rule, so that you know that P is point to this direction, and then the E field point to that direction, so that you have something like this, and then you cross product, so that the torque should be pointing into the page. So we have we can draw it like this. We have a cross, which means that the torque point into the page. And you can suppose that there is a potential energy. Potential energy is P inner product with the E, inner product with the E. So it is something like if P and E has the same direction, which means that it is very stable because this one will stretch to the right side, this side will stretch to the left side. So it will be very, very stable. So you have the least potential energy, which means that theta is 0, this time is 1, this time is 1, so that the U is minimized. U is minimized. If theta is 180 degrees, which means that if the dipole onto the left side, it will be very unstable because this point we try to go to the right side, this point we try to go to the left side, so that it will jump, something like this. And as you know that cosine should be between 1 and 0, so that you can imagine it will be something like this one will be between minus PE and plus PE. And actually, you can imagine an energy case. So if you have a curvature like this, and then you put a ball here, and then you put a ball here, then the ball, if you assume there are no friction force, the ball will go down, assuming it is original stationary, then the potential energy will turn to the kinetic energy, so that the kinetic energy is maximized, and then the potential energy U, so U will become minimized. So it has a very large kinetic energy, so that will go up to here. And then all the kinetic energy will turn to potential energy. Something like this. So imagine you have a E field here. And then if you have a dipole, P onto this direction, you will just stop there. And if it is something like this at the very beginning, assuming it is stationary, then you will something like something like this. You swing back and forth like this case. So any question regarding to this one or up till now? Okay, so let's have a additional example. So this one, a clock face has negative point charge, negative Q, negative 2Q to negative 12Q fixed at the position of the corresponding numerals, which means that you can imagine the clock there. So at the number 1, it has a charge negative Q. At the number 2, it has a charge negative 2Q. And up to the 12, you have a negative 12Q, something like this. So the clock hands do not disturb the net field due to the point charge. At what time does the hour hand point in the same direction of the electric field? Which means it's just trying to ask you what is the direction of the E field generated by all the point charges. So it will be quite simple. So actually, you can imagine if you have a charge at 1, which is negative Q, and at 7, which is minus 7Q. So in this case, the negative Q charge will generate an E field pointing to the 1. And for the minus 7Q, it will point to the 7. But this is 7 times larger because E is equals to K times Q over R squared. Actually, R squared is the same for all the numbers, right? Because all the numbers with the same distance to the center of the clock. So R squared should be the same for all the 12 charges. So the only difference is the number of charge amount. So for this one, -1, this one is -7. So actually, so actually part of the electric field should be cancelled. So you can imagine it is equivalent to only have -6 charge, -6 Q at the number 7, right? And for 2 and 8 is the same case. 2Q minus 2Q can be cancelled. So we have the number 8, we have -6Q, and for 9, -6Q, for 10, -6Q, 11, -6Q, 12 also -6Q. So we only have -6Q on this 1, 2, 3, 4, 5, 6 number. So in this case, the E field should point to the direction which is between 9 and 10. 9 and 10. Which means it should be 9:30. I should speak quicker so that the clock will also point to 9:30. Okay, so so let me also finish this one, and then we will have a short break. So for this one, suppose you design a apparatus in which apparatus是仪器的意思。In which a uniform charge disk of a radius r produce an electric field. The field magnitude is most important along the central perpendicular axis of the disk. At point P, at the point P at the distance 2r from the disk, which means this one is 2r. The radius of the disk is r. And the cost analysis suggests that you switch to a ring of the same outer radius r, but with an inner radius r2. So this ring is a bit different from the ring we discussed previously. The ring we discussed previously is a very thin ring, but for this ring it is a very large radius, which is r/2. So assume that the ring will have the same surface charge density as the original disk. You switch to the ring. If you switch to the ring, by what percentage you decrease the electric field magnitude at P? Which means that you assume that you have some charge on the disk, and then you just remove the inner circle, and then the charge at this inner circle you also remove. So the total charge on the disk will be different, but the density on both cases should be the same. So which means that if we have the same charge density for both cases, we can assume it to be sigma. Assume it to be sigma. We don't need to separate sigma 1, sigma 2. So for this case, maybe we can call it A. We call it E. So EA should be sigma over 2 epsilon 0, 1 minus 2R. Z is 2R over Z is 2R. 2R squared plus R squared. Something like this. So this is the E field generated by the solid disk. We only have Z equals to 2R. Z equals to 2R. So in this case, R and R can be cancelled. So finally, we have sigma over 2 epsilon naught 1 minus 2 over square root of 5. And for part B, it will be switch to ring by the water You will decrease. B means the charge regarding to the inner circle. So that EB should be sigma 2 epsilon 0, 1 minus also 2R, which is the Z. So over 2R square or plus R over 2 square. So because the Z should be should remain the same, so this is still 2R. So this is still so this is still 2R. The only different part is this one, which is 1/2. And actually it is the radius of the inner circle, inner radius. So for this case, this one should be sigma over 2 epsilon naught 1 minus 4 over square root of 7. So finally, we can have EB over EA to be 1 minus 4 over square root of 7 all over 1 minus 2 over square root of 5. And then sigma over 2 epsilon naught will be cancel each other. Then we multiply by 100%. So actually it is 28.3%. 28.3%. So actually you reduce the E field generated at this point by 28.3%.